Good morning, students. Today we are starting with modern physics. So, first of all, in modern physics, we will be knowing about what do we mean by metals. So, metals are those substances which can emit the electron. Now, the emitting of electron in our chapter we are dealing basically when a photon of suitable frequency is incident on any metal surface, then the equivalent electrons will be emitted. But before that, we have to see some important thing. Like if I say that the free electrons are present on the metal surface, it means that the free electrons which are actually present on the metal surface are not free to move in the nature. These free electrons can only move in their lattice, means they are free to move along the metal surface but they cannot move in the environment. But if we have to eject these free electrons from the metal surface, then here in this chapter we are going to discuss the same part. The chapter is Photoelectric Effect. So here we are going to deal with how we can emit the free electrons from the metal surface. Now for that there is one important term that we have to discuss. The important term here is work function. So what is work function? So work function is denoted by phi naught, and this is actually the minimum amount of energy required by the metal surface to emit electron. Now the work function is that minimum energy which we require to remove the surface electron. Now afterwards, when this electron is emitted, now there are two cases possible when the electron emitted has additional kinetic energy along with it, or if the electron is just emitted and it has zero kinetic energy. For example, the work function of a metal is 330 electron volt. Now if we had provided the work function, or we have provided the energy of 31 electrovolt, this means that the 30 electrovolt will be consumed by the electron to get out of the surface, and the kinetic energy of 1 electrovolt will still persist. Whereas if we are just providing the amount of work function that we require, and that is 30 electrovolt energy, in this case the net kinetic energy that is afterwards the electron has is zero. So here we can say that electron will have no kinetic energy. We have to also learn that the work function is unit is electrovolt, and this electrovolt, 1 electrovolt is equal to 1.602 into 10 to the power minus 19 joule. This is the 1 electrovolt value. Now if we talk about the work function of various metals, so cesium has the highest work function, that is about 2.14, and the platinum has the least work function. Means if I say that cesium has the lowest work function and platinum has the highest work function, it means that very less work function is required by cesium to emit out electron. Means for the photoelectric emission to take place, cesium require the least work function but the platinum require the highest. Means you have to at least provide 5.65 electrovolt energy to the platinum surface so that an electron can be emitted out. Now there are electro emission steps also which we have in our syllabus. So we are now dealing with the electron emission, and now in this part we are going to see the various steps of how we can emit the electron from the given surface. Now what is the meaning of electron emission? So it is the phenomenon of emitting the electron from a metal surface. This will be referred to as electron emission. Now there are various methods, like the first one is the thermo-ionic emission. Now this thermo-ionic emission means that when we are emitting the electron by giving excess of the thermal energy, and the electrons emitted will be thermo-ions or thermo-electrons. The another one will be the field cathode emission or field emission. Now this describes that when we provide an electric field to any of the metal surface, then the electrons will be emitted, and this electric field value is 10 to the power 3 to 10 to the power 8 volt per meter. Means we have to provide at least this much of the electric field so that we can emit the electrons. When we talk about the third one, we have the photoelectric emission. Now this photoelectric emission is what we are going to discuss further in this chapter. When we are providing the EMW, that is electromagnetic waves, it will contain some photons, and these photons have the equivalent energy which the electrons also require to get emitted, and this equivalent energy is consumed by electron to just emit from the surface. The last one is the secondary emission. Now what is the meaning of secondary emission? So this is very simple. When the fast moving electrons, now we are dealing our concern with the fast moving electrons which are not present on the metal surface. Now when these fast moving electrons strike the metal surface, so on striking, what do? They generally these electrons transfer their energy to the metal surface, and when they transfer their energy, the free electrons which were present on the metal surface, they gain this energy and then they escape out, and the free electrons that are escaping out are also known as secondary electrons. And this whole process is called as secondary emission because the second electron is escaping out when the primary electron was from the outer metal surface. Now we will discuss the process of photoelectric emission. So the next topic is actually photoelectric effect. Now here we are going to first see some scientists and their observations. What were their observations? So first scientist that we are dealing with is Herd's observation. Now what does he see? So when Herd observed that on a detector loop, when we passed some of the sparks are basically high voltage waves. So when these sparks were produced, and now these sparks, on the other hand, when we see that the same detector loop whose cathode was illuminated by UV light, now when we see that the spark loops which are produced were more fast and were more easy to transmit, and this was just taking place because the sparks were just going on at a very higher rate because of the emission of the electrons. As we pass the UV rays to this metal surface or this detector loop's cathode, the cathode emitted electrons, and these electrons enhance the high voltage or that spark. Now let's discuss the next one, that is the Hallwalks and Lenard's observation. So they saw that a zinc plate, when the zinc plate was placed here, and afterwards when this was also connected to a electroscope. Electroscope is an apparatus which is used to detect the presence of a current or a charge. So the leaves are actually, basically the leaves are like this, but when the charge is there, so these leaves are like this. So when we gave some of the radiations to the zinc metal, then what happened basically was that the leaves were pulled apart. These leaves pulled apart, and this proved that because some charge was developed, and this charge was due to the electrons which were emitted from the zinc plate. So we can say that because of the zinc plate, the leaves were pulled apart, and this was Olbach's and Lenard's observation. And afterwards, they also produced the photo current, or we can say that the photoelectric current. Now, how was it produced? So it was based on the same way that we have done just now. What they do was that they took one circuit which was connected with a battery, and also there was one bulb or one ammeter which was located over there, and there was one apparatus where one cathode which can emit, which had a low work function, and one anode was present which were not connected, and they were evacuated. Now when the suitable radiation light fall on this, the electrons were emitted which moved on to this anode part, and because of this electrons, the current was able to flow, and the ammeter showed the deflection. So this was the production of the photoelectric current. So now we are going to start the basic conclusion. First, let us derive what is the basic conclusion that we have seen till now after the observation of Hertz and then Olbach's and Lenard's. So we saw that the phenomenon of emission of electrons from the metal surface when electromagnetic radiation of sufficiently high frequency are incident are called as photoelectric effect. Now let us see one important one, that what do we mean by potential. Now afterwards, when we see the another type of important concept is related to potential. Now this is very simple. Here we have to just see that when on the plates A and B, when this plate A is, suppose it is cathode, and this is illuminated by a suitable light frequency which can at least emit the electrons, means it is having that work function. Now what is there? This B plate is now subjected to the change in potential. Now when this B plate is subjected to change in potential, what do we see? At the first case, when we were increasing the potential, so the A plate, because in order to maintain the same potential, the A plate injected more and more electrons, but after that a potential came when no more electrons can be ejected from A plate, and all the electrons were collected to B plate. And at the second case, when we decrease this potential, so the electrons from the B started moving at the reverse direction, and the same point came when now no more electrons were remaining on the B plate. So this was all due to the potential difference that we created, and this was the effect of potential on the photoelectric effect. Now when we see the effect of intensity on light on the photoelectric current, so now let us discuss that. So basically, according to Millikan's experiment and Lenard's experiment, we saw that there was one evacuated tube which had a quartz window, and there were the cathode and anode similarly placed over there. This was the cathode part and this was the anode part. Now when the radiations were falling on it, the electrons were emitting and were moving on to this plate. So this we already know. Now when we talk about the intensity is directly proportional to frequency. Means if you are increasing the intensity of light, it means that the frequency of the incident light is also increasing. Means as the frequency of incident light is increasing, now the more electrons are emitted. Now as more electrons are emitted, we can say that the photoelectric current is also increasing with the time. So this was an important information that I have to provide to you. And here when we plot the graph for the photoelectric current as well as the intensity, we find out that the graph is linear, which easily proves that, and it starts from the zero position. It is actually the linear graph. If I say, to be more honest, then the graph plot will be exactly linear, and this will prove that the photoelectric current is directly proportional to intensity, and this intensity is further on directly proportional to the frequency. At the same time, when we were talking about the effect of potential, the graph obtained is slightly different. When we see over here, this is the graph which is plotted for the effect of potential, and here we observe that the three intensities we are comparing. So first of all, in the graph we have at one side we do have photoelectric current, and the other graph we have the anode potential and the retarding potential. Now over here, when we observe, we see that intensity 1 is smallest out of all the three. Now when we look at this point, we observe that after a certain time only the photoelectric current will start. This is already in context to the work function, because when we are providing the work function, after that time only the photoelectric current is seen. This is an important phenomenon, that at the work function, after work function is achieved, we are able to observe photoelectric current. So that's why we have to at least achieve this state, and we can see that we cannot start from the zero position. And if before that we see that retarding will go to the minus V0, that is the retarding potential. This is the value of retarding potential at which the photoelectric current becomes zero. It's called the cutoff or the stopping potential. Means at this time we have the zero photoelectric current. Because it is not here, if we extrapolate the graph, we see that we are obtaining our final expression over here. So this is our V0 minus B0, which is our retarding potential, and this is where the photoelectric current is 0. So we can see over here that for a given frequency of incident radiation, the stopping potential is independent of intensity, and in turn it implies that the maximum kinetic energy of the photoelectrons is independent of intensity of radiation. So the maximum kinetic energy we can also write as So when we talk about the maximum intensity of the photoelectric kinetic energy, so we can write it as K max equal to half of mv square maximum. Means, so this was actually kinetic energy maximum, and this maximum kinetic energy will be equal to half of mv square maximum, and this will further be equal to ev naught, and this ev naught is actually the work function that we have to provide, and this can be also equal to the maximum kinetic energy that is also achieved by the particle. So this equation you have to learn, because this is very important.